Hello and welcome to Lead Programmer. Today we are going to solve the question number of enclaves. So we have a binary matrix grid. Binary matrix means the matrix consists of only 0 and 1. Here 0 represents a C cell, 1 represents a LAN cell. Now they have defined a move. So what's a move? So let's say we are at this LAN cell. So from this LAN cell we can either go right, we can either go left, we can either go down, or we can go up. So that's a move. But a valid move would only be from one LAN cell to another LAN cell. We cannot go from one LAN cell to a water cell or from a water cell to a LAN cell. That's not a valid move. Now the objective is to return the number of LAN cells in the grid for which we cannot walk off the boundary in unlimited number of moves. So how many ever times we move, we shouldn't be able to walk off the boundary. So let's look at the example one. So if we look at this particular LAN cell, we can easily walk off the boundary, right? If we look at this LAN cell, okay, from this LAN cell we can either go to this LAN cell, from here we can go here, but then we are stuck, right? There's no possible move in this particular cluster using which we can go off the boundary. Hence the answer over here is 3, because for these 3 cells we cannot walk off the boundary no matter what. So if we do a breadth first or depth first search here, we do not reach the boundary. If we do a breadth first or depth first search here, we do not reach the boundary, and same for this cell. Hence the answer over there is 3. Let's look at another example. Over here, if we do a breadth first search here, we can easily walk off the boundary. Same applies to this case. Same applies here. So if we do a breadth first search or depth first search here, we can walk off the boundary. If you do a depth first or breadth first traversal here, we can also walk off the boundary. So hence here the answer is 0, because for all the cells we can walk off the boundary, but the objective is to return the number of cells for which we cannot walk off the boundary. Okay, so now that we understand this, let's look at what the way of solving this should be. It is kind of hinted from the way I went with examples. So we just go through the entire grid and we care only about the LAN cell. So if we encounter a water cell, we just skip. So we just skip all these. And if we encounter a LAN cell, okay, for the LAN cell, we do a depth first traversal or a breadth first traversal. It doesn't matter. Any type of traversal would work. But if we reach off the boundary, or we reach the boundary during the traversal, then we know that particular cell will not be counted in the solution because we can walk off the boundary. So if you do a depth first or breadth first search here, we know we can walk off the boundary, hence it's not counted in the solution. In this, as we saw before, it's if we do a depth first or breadth first search, we cannot reach the boundary, and hence it's not counted in the solution. So that's one solution. That's one way to solve it. So we just keep doing breadth first, depth first search for each LAN cell and keep track. But I like another way, which is a smarter way to look at this question. It's a different way of viewing the question. So let's reverse our thinking. Let's go to the smarter way. Let's reverse our thinking. So one thing we notice is for all the boundary cells, so these cells refer to the boundary cells, for all these boundary cells we can walk off the boundary. So all the boundary cells, from all the boundary cells we can walk off the boundary. Now if from a boundary cell we can go to an internal cell, so I'm referring to all the cells which are not boundary cells as internal cells. So if from a boundary cell we can have a valid move to go to an internal cell, then we know that that internal cell can also reach the boundary in any number of moves. So if we encounter a LAN cell in the boundary, then we try a depth first or breadth first search from that cell, and all the cells that we encounter cannot be considered in the solution because we can walk off the boundary from all of them. So in this case, if we do a breadth first or depth first search, we just stay here. So that's fine, but we know this particular cell is not counted in the scenario. And that's it, because all others are water cells and we do not care about the water cells, so we ignore them. And at the end, we know that we just have these three internal cells remaining. So that's the answer. Whereas in this question, we see, okay, as soon as we encounter this particular cell, we do a depth first search and we reach all these cells, and we know that all these cells will not be included in the solution because we can walk off the boundary from them. So essentially, the idea is we start from the boundary cells. For each boundary cell, which is a land cell, so a land cell at the boundary, we do a depth first or a breadth first search, and all the cells that we encounter during the traversal, we convert them to water cells because we don't care about them. We do not care about them in the solution. After that's done for all the boundaries land cells, at the end we just count the number of remaining land cells in the solution. So for example, in this case, if we do a depth first search, we convert this to a 0, we convert this to a 0, we convert this to a 0, we convert this to a 0. And at the end, we just count the number of remaining land cells. How many land cells are available? None. So the answer is 0. So let's see how to implement the smarter way, because that's easier to implement. And faster, much faster. So we have a main function, number of enclaves. We have a result variable, and that's the one we returned. It keeps track of the number of land cells. We just represent water and land by 0 and 1. We go through the entire grid, and we care only about the land cells. So that's the check we do first. And another check we do is we only care about the boundary cells. So we see if the cell lies at the boundary. How do we check that? So I represents rows. So if it's the 0th row, or if it's the last row, that's I equals 0, or I equals the length of grid minus 1, or the column, it's the 0th column, so j is 0, or it's the last column, so that j is length of grid at 0 minus 1. So if that's the case, we call either a BFS or DFS, and that BFS or DFS will change the grid and appropriate land cells to zeros. For now, let's assume that that's good. So after all that is done, after this block is done, we move on to this block where it's pretty simple. We just go through the grid and count the number of land cells. We increment res if we encounter a land cell, and that's what we return at the very end. So now let's look at both BFS and DFS. So I'm assuming you guys know what BFS DFS is, like a general idea of it, and how to basically implement it. Let's quickly walk through the through a quick idea of what BFS or DFS is. So let's say we have a graph like this. So a DFS on this particular graph would be, okay, we first come here, then we come here, we come here. So we explore the depth first, and then we might come here, and then we might come here. So we first go to its depths first and then explore the rest. So that's what a depth first search is. Now let's do a breadth first search on the same example. So this was the example that we had. For a breadth first search, we essentially start here. Okay, so this is the first node. Now we go through all its neighbors. We want to explore the breadth first. So we do 2, 3, 4. So we explore its neighbors first. So we explore the breadth first, and then we move on to the next level over here. So that's the general idea of breadth first and depth first search. Great. Let's look at the depth first search solution first. So we pass in the grid, we pass in I and J. I and J was passed here. That's the location of the land cell we are running the DFS on. And then we just pass how land and water are represented. So if a cell that we encounter is not land, if it's water, then we don't care about it, we just return. But if it is land, then we want to convert it to water, because remember, for each cell we encounter, it cannot be in the solution, because for that cell we can walk off the boundary. Hence, all the cells that we encounter during our traversal should be converted to water, as stated earlier. So we convert the land cell to a water cell here, and then we want to explore the neighbors of that particular cell. So first, and we want to ensure that those neighbors are valid. For example, let's say we are at the boundary where I is 0. So we cannot pass in I as -1 because that's an invalid location. So we want to check if the index we're passing is valid. So for that, we check if I minus 1 is valid. If I minus 1 is valid, then we call the DFS. We do a recursion, we call the function again. If not, we just don't. Same thing for I plus 1, same thing for j minus 1 and j plus 1. And we do the same thing and we pass in the indexes as appropriate. And that's it. That's the DFS solution. Let's also look at the BFS solution, which is very similar, but I've implemented it in a bit of a different way. Let's look at it. So breadth first, again, we explore the breadths first. So we go level by level. So we explore, so if we have a cell, we look at all its neighbors first, and then the neighbors of neighbors, and then the neighbors of neighbors, and so on. Great. So how do we implement a BFS? We do it using a queue. So let's first populate the queue by the starting indices. So we put in I and j. So while the queue is not empty, we look at a level. There we pop in the index. So A represents I and B represents j. So we first check if the obtained index is valid. So we do it by A should be greater than equal 0, B should be greater than equal 0, A should be less than the length of grid, and B should be less than the grid of 0. So we do that, and we care about if the grid is a land cell or not. If it's not a land cell, we just continue, we just don't care about it. And if it is a land cell, then we convert it to a water cell. And if it is a land cell, then we also care about the neighbors of that land cell. Hence, we come here where we just have an array visitor, and we have all the neighbors here. So a minus 1b, a plus 1b, a b minus 1, a b plus 1. So all these are the neighbors of a and b. We just put them in an array called visitor, and we just append all the elements in that visitor. We could have also done q.append 4 times, but this is just another way to do it. We could have also checked the validity of the index before inserting it into the queue. That's just another way to solve it, but here we did a check over here. So if we don't do a check here, then we have to do a check before we insert it into the queue. Yep, so that's the BFS solution. Let's look at the time complexity. So the time complexity of this part is the big O of nm, where n represents the number of rows, m represents the number of columns. So we go through each and every cell. So that's the big O of nm, which is linear to the number of cells in the grid. And over here we go through all the cells and we do BFS. So it might seem worse than linear in this case because we have a nested for here, and we call another function which goes through potentially many cells, or potentially all the cells. But one thing to note is we convert cells from land to water, and we just ignore water cells. So effectively we go through the entire grid only once. So this would also be linear to the number of cells in the grid, so O of nm, and hence the overall time complexity of this solution is linear, since O of nm plus O of nm is equal to the O of nm according to the rules of time complexity. Or okay, so I hope you found this helpful. Please subscribe to the channel. Thank you.